Neptune has a mass of 1.02 times 10 to the 26 kilograms and a radius of 2.48 times 10 to the 7 meters. We'll treat it as a uniform solid sphere. The distance of Neptune from the Sun is 4.5 times 10 to the 12th meters, and assume that it completes a single rotation in 16.1 hours, orbiting the Sun every 5.98 times 10 to the 4th Earth days. They want us to find the angular momentum of Neptune in its orbit around the Sun. All right. So Neptune has a velocity at the current time, which is going to be roughly 90 degrees with the position vector, because the orbits are roughly circular, a little bit elliptical, but let's say it's treated as circular for now. So here's R, and we'll call this the momentum vector P. Now we want to find angular momentum, so one of the formulas is L equals R cross P. But there's another formula too. L equals I omega, and either of those can give us the answer. We know how long it takes to complete the orbit. Period of the orbit is 5.98 times 10 to the 4th days. I'd rather get that in seconds though. Day is 24 hours. 3,600 seconds in an hour. So the period of orbit then is 5.17 times 10 to the 9. Seconds. Alright, so we have the formula that omega is 2 pi over t. Therefore, we can find the angular speed. It'll be 1.22 times 10 to the minus 9. Units will be radians per second. Alright, so that actually helps us get somewhere with this formula. But we need the moment of inertia. And it's like, do you use the moment of inertia of a sphere? Or do you use the moment of inertia of a point mass? And the answer is, you treat it like a point mass. It's rotating as if it's just like one point, just like a rock on a string. But that's only for this part of the problem. There's other parts of the problem where we would treat it as a sphere. So you'd use the formula mr squared then. We have the mass 1.02 times 10 to the 26. But we need the distance in meters. Let's see, what can we get the distance? Oh, it's given right here. 4.5 times 10 to the 12 meters. Yeah, we have to square the radius. Okay. I get 2.51 times 10 to the 42 kilogram meters squared per second. And we want the other formula to tell the same story. Alright, so we're going to need R cross P for that. But notice that there's 90 degrees between R and P. So it just simplifies to R times P. Alright, so how do we find P? P is going to be the mass times the velocity. So we'll have that. And we can find the velocity from the formula V equals R omega. So if we were to substitute that in, I guess we would get L equals R times M times R omega. And you can see what's happening here, right? mR squared omega, which is the same thing as up here. So it's the same either way. Alright, so the last thing to do is to find the angular momentum of Neptune spinning on its own axis. And for that, we would now treat Neptune as a sphere. And you'd use the same formula, L equals I omega, but now it would be the eye of a sphere because the thing is going to be rotating. Like all the mass is going around this axis of rotation, which is in the center. So, moment of inertia of a sphere from tables of moment of inertia would be 2/5 mR squared. And then we have to multiply by the angular speed, but of the planet, not the orbit. So what's the angular speed of the planet? They say it takes 16.1 hours to rotate. So now my period of rotation is 16.1 hours. Let's change that into seconds. 3,600 seconds in an hour. 57,960 seconds. Therefore, the omega of rotation will be 2 pi over t, which is 2 pi over 57,960. 1.08 times 10 to the minus 4. Radians per second. So we can plug that in here. Now, I'm just finding the magnitude of the angular momentum here. We gotta put in the mass of the planet, which was 1.02 times 10 to the 26. Radius of the planet, 2.48 times 10 to the 7 meters. Square that. Alright, let's see what we get. 2.71 times 10 to the 36, I believe, kilogram meters squared per second.